All right, let's talk potential energy diagrams. All right, so potential energy diagrams show changes in energy during a chemical reaction. They're different for endothermic versus exothermic reactions. So just as we look a quick overview here, you can see for this endothermic reaction, here are the reactants and here are the products. And we're looking at exothermic. Here are the reactants, and then over here are the products. What you can see is just a general trend in the shape of the potential energy diagram. It always goes up from reactants, okay? And it reaches a top, and then it always goes back down until it gets to the products. The difference is that for endothermic, the reactants are lower in energy than the products. And for exothermic, the reactants are higher in energy than the products. So let's go through it. In an endothermic reaction, energy is absorbed. So that means the potential energy of the products is greater than the potential energy of the reactants. Overall, the amount of energy increased from reactants to products. Whereas in an exothermic reaction, the potential energy of the reactants is greater than the potential energy of the product. So energy is released. So when we compare the potential energy of the reactants to the products, it goes down. All right, let's look at some specifics. So you should be labeling your diagram. Here is the representation of the potential energy of the reactants. Reactants are what we start with. So the potential energy of the reactants for this reaction is 45 kilojoules. What about products? Well, the products are what we end with, so over here. So in this reaction, the potential energy of the products would be 10 kilojoules. What about the activated complex? Well, the activated complex is the tippy top. Okay, so all the way up to there. So you start from the bottom and you get all the way to the top. So the potential energy of the activated complex would be 103 kilojoules for this reaction. Now, activation energy, what is that? That is the amount of energy we need to get the reaction started. Now, the reaction starts with the reactants. Okay, it ends with the products, but it's not a direct line. It doesn't go like this. Does not do that, right? It has to go, so it does not do that, right? What does it do? It goes up here. So the activation energy is what we need to get to the highest point. So we start at reactants, but we got to get to the tip top before we can form the products. So the reaction has to follow this path. It has to go from reactants and start to add energy and add energy and add energy and add energy until voila, we make it to the activated complex. Then the reaction continues and the products will form. Okay, so the activation energy takes us from the reactants where we started to the very top, the highest amount of energy we need. That's what we need to get the reaction started. If we don't add enough, the reaction doesn't happen. We have to get all the way up here. So in this case, that means 103, which is the highest, minus the reactants, what we started with. So the activation energy is 58 kilojoules. If 58 kilojoules are not added, the reaction does not proceed. Now, the next major concept is the heat of reaction. The heat of reaction is found by taking the energy of the products minus the energy of the reactants. It's important for the order, okay? So you have to do products minus reactants. So in this case, it is 10 minus 45, which gives me a negative 35. Why does that matter? This was exothermic, remember? Exothermic reactions should have a negative change in energy, which we have already learned before. So it all makes sense. This is where it's represented. It's the difference between the products and the reactants. So in between them, okay? So for the heat of reaction, the delta H, the order matters. You have to do products minus reactants. End of story, period. Always do it that way. If your reaction is exothermic, it will always be negative. If your reaction is endothermic, it will always be positive. Okay? All right, so let's look at this reaction. What do you think? Does this potential energy diagram show an exothermic or an endothermic reaction? Yeah, it's exothermic. How do I know? The products are lower. It goes down, okay? What would the potential energy of the reactants be? Well, where are the reactants? Over here, right? So it would be 40 kilojoules, yes. What would the potential energy of the products be? So think about where the products are. They're over here. So what would the potential energy of the products be? Yeah, 20 kilojoules. Now, what about the potential energy of the activated complex? Do you remember where that is? All the way at the tip top. So what would the potential energy of the activated complex be? Yes, 100 kilojoules. Now, do you remember, what would the activation energy be? Do you remember what we have to do? Well, we have a certain amount of energy that we started with. That's where we are with the reactants. And where do we have to get to for this reaction to proceed? Right to the top. So the activation energy takes us from where we started with the reactants all the way to the highest point. That's where we need to get to. So what would it be? Well, we would do 100, the top, minus 40, where we started, and you would get 60 kilojoules. Now, what about the heat of reaction, or delta H, or the change in energy? So those are ways you might see it represented. How do we find that? Remember, it's products minus reactants. The order matters. So on the diagram, it's represented here, but what would the value be? What would our number answer be? Yes, 20 minus 40, products minus reactants, and that would be negative 20 kilojoules, which makes sense because it is exothermic. The delta H should be negative. All right, so putting it all together, we have reactants, what we start with, products, what we end with. We have the activated complex all the way at the tip top. We have the activation energy that takes us from where we start at the reactants all the way to the tip top. And then for our delta H, or change in energy, heat of reaction, that's another way you'll see it. It is the difference of products minus reactants, and it will always be represented by that space, the gap in between products and reactants. Now, sometimes you're asked about the reverse reaction, okay? What do I mean? Well, we talked about the reaction going forward, right? So here we start with reactants, we add energy, we add energy, we add energy, we get to the activated complex. And then as the reaction proceeds, energy is released until we are at the energy level for products. So looking at that reaction for the forward reaction, would this reaction be exothermic or endothermic? Yeah, it would be exothermic. Now, what about the reverse reaction? Well, for the reverse reaction, all we do is say, instead of starting here, I start over here, and I follow the same path, but I end over here. So this is reactants, and this is products. So with that reverse reaction going like this again, right? Would that be exothermic or endothermic? Well, it would be endothermic. Now that should make sense. If one is releasing energy, going in the opposite direction has to be absorbing energy. Like you can't walk uphill both ways, right? Now, we can read potential energy diagrams according to this reverse reaction. So the first thing we do is kind of swap what we're thinking about where products and reactants are. So what would the potential energy of the reactants and products for the reverse reaction be? Well, we just swap where we're thinking about it. So the potential energy of the reactants would be 200. The potential energy of the products would be 400, both in kilojoules, okay? What would the potential energy, the activated complex be? Well, the thing is, it's the same. Now, let me make a note about reverse reaction. If you're ever asked about a potential energy diagram, always assume they're talking about the forward reaction, the regular way. Now, only time you have to worry about reverse is if the question specifically says reverse. If it doesn't say reverse reaction, they mean the forward. Okay, so now back to the activated complex. For the forward reaction, I would start here, get all the way up to the top, and then go back down over here and end at the products. For the reverse reaction, I'm starting here, but I still have to get all the way up here, right? And then it would end over on this side. So the potential energy of the activated complex is the same, right? It would be 500, no matter if I'm talking about forward or reverse. The letter that it's representing is C, okay? What about the activation energy of the reverse reaction? Well, this is definitely different because we're starting and ending at different parts, right? So the activation energy of the reverse reaction is still going from reactants to the tip top, but we're starting at a different part. We're starting over here, right? And we have to get up to the very top. So you would have to do 500 minus 200, okay? There is the representation of that activation energy. Now, delta H, heat of reaction, change in energy, is always products minus reactants. So you have to think, where are the products? Well, the products are 400 minus the reactants. Those are 200. So I'm going to get a positive 200, which makes sense because this reverse reaction was endothermic, so that delta H should be positive. Okay, so here's a question. Is this exothermic or endothermic? Well, it doesn't say reverse reaction, so we assume forward, and that is endothermic. It goes up. What about this one? Endothermic or exothermic? Yeah, exothermic, it goes down. All right, one last thing. What is a catalyst? Okay, well, a catalyst starts at the same spot, reactants, ends at the same spot, products. But it's like a shortcut. So we're going to get there faster. Okay. How does it do that? Well, a catalyst lowers the activation energy and it provides an alternate path. So here is my original path from reactants to products. I add a catalyst and it still goes from reactants to products, but you see how it's lower? Okay, so the activation energy goes down. I need less energy to get started. It makes the reaction happen faster because I need to put in less energy for it to occur. Okay. Now, a question they like to ask a lot is using table I to draw a potential energy diagram. Okay. Now this says draw a potential energy diagram for the synthesis of aluminum oxide. So first I need to find aluminum oxide synthesis in table I. And remembering that a minus sign, this is from the bottom of the table, indicates an exothermic reaction. So here is the synthesis of aluminum oxide. Look at that heat of reaction. It's negative. So what does that mean? So that means when I'm drawing the potential energy diagram, here are the reactants. I have to follow a path where I make a bump that goes up, and then it's exothermic, so it has to end lower. So there's my quick sketch. It has to look something like that, right? All right, so given the potential energy diagram representing this reaction, which numbered interval represents the heat of reaction? So which number shows the heat of reaction? Yeah, it's 2. It's the difference between the products and the reactant. Let's see if you can figure out the rest. Which number shows the potential energy of the products? Yeah, it's 4, right? Which one shows the potential energy of the reactants? Yes, it's 1. Now, does 3, which is the only one left there, does 3 show the activation energy of the forward reaction or the activation energy of the reverse reaction? Yeah, it's the reverse, because here's the forward going this way, right? All the way up here. So we're endothermic. Activation energy would be this. It's not even numbered, right? So in order to get that, I would have to do 2 plus 3. But the reverse reaction starts here and ends over here. So its activation energy is just that piece. There you go. Whole bunch about potential energy diagrams. Should make sense.